Hey there! Welcome to Math Foundations for Microeconomics. In this video, we'll explore the essential math concepts that will lay the groundwork for your success in microeconomics. While microeconomics might sound like it's only about ideas, math plays a crucial role. It helps us build models, analyze trends, and make precise predictions about how markets work. This video isn't meant to be a comprehensive math course. Our goal here is to review the core math concepts you'll encounter repeatedly in your microeconomics studies. Okay, let's look at the road ahead. We'll begin by looking at if one can even do microeconomics without math. We'll start with some practical stuff like area calculations, then we'll get into the heart of it with functions and their graphs. This is how we visualize economic relationships. Slopes and intercepts tell us how much one thing changes when another does. Equations let us put those relationships into a super compact form and work with them. And finally, a peek at calculus, not always needed for basics, but it powers up your economic analysis. Okay, let's be real. Can you completely avoid math in microeconomics? Technically, yes. You can grasp the general ideas of how markets work, consumer behavior and such, but here's why math matters. Think of it as the ultimate power tool for economists. It lets you turn vague ideas into precise models. Graphs aren't just for show, they visually represent mathematical relationships. Equations let us pack a whole economic model into a few lines and play around to see what if the price changed or what if a tax was introduced. The good news is you don't need crazy advanced math for a basic course on microeconomics. A solid understanding of algebra can take you far. And if you're planning to go deeper into economics, learning some calculus definitely gives you an advantage for understanding more complex models. Alright, let's get started. You might be surprised, but even calculating area is relevant. Let's dive into our first area calculation, the rectangle. The length is the horizontal distance across and the width is the vertical distance. The area tells us the total amount of space this rectangle covers. Why do we multiply the length and width to get the area of a rectangle? Think of the rectangle as a giant grid of tiny squares as seen here. If the length is 6 squares long and the width is 4 squares tall, we have a total of 6 times 4, 24 little squares filling up that rectangle. That's the area. In other words, multiplying length by width gives us the total number of square units that fit perfectly within the rectangle. Next, let's look at right triangles. Imagine we take our rectangle from the previous slide and cut it diagonally in half. We now have two right triangles. The base of this right triangle is the same as the original rectangle's length, which is 6 units. The height is the original rectangle's width, which is 4 units. The key here is that for a right triangle, we only consider the base and the height that creates the right angle or 90 degrees, not the hypotenuse, which is the diagonal side. The formula for a right triangle's area is half multiplied by base multiplied by height. In this case, it's half multiplied by 6 times 4, which equals 12 square units. So each of these right triangles has an area of 12 square units, which is exactly half of the 24 square units we obtained for the rectangle in the previous slide. But what about triangles that aren't right angles? No problem at all here. There are two ways to tackle this. The first approach is easier to visualize. We can imagine cutting this triangle into two right triangles just like we did with the rectangle. As long as we draw the height from a vertex perpendicular to the base, we'll create two right triangles. Then we can find the area of each right triangle using our familiar formula, which is half multiplied by base multiplied by height, and add those two areas together to get the total area of the original non-right triangle as shown here. So that would be half multiplied by 2 multiplied by 4 plus half multiplied by 4 multiplied by 4. So that gives you a total of 12 square units. Or there's actually a shortcut. We can use the same exact formula, half multiplied by base multiplied by height, for any triangle, not just right triangles. The key here is that the height h must be perpendicular to the base. So in this picture, the base is the whole horizontal line at the bottom, which is 6 units, and the height is the vertical line going down to meet the base at a 90 degree angle. So the height here is 4 units. So in our calculation, that's half times base times h, half times 6 times 4, which gives us 12 square units. Okay, now let's move on and talk about functions and graphs. They are the heart of how many economic models work. So what's a function? At its core, a function is a rule that describes a relationship between two things. Sometimes it's a simple definition, like professor is equal to Joe. Here, professor depends on a single thing, who's teaching the class. But functions get really interesting in economics when they show cause and effect. Let's say your final score in this microeconomics class depends on a few factors: your exam grade, class participation, and assignments. We can write that as a function as shown here. Notice how your score is on the left side. It's the thing that is being determined. On the right side, we have the factors that influence your score. Functions are all about how different things are connected. In your microeconomic course, many of those relationships will end up looking like this: y is equal to b plus mx. We'll be dissecting this type of equation a bit later in this session. Alright, now let's understand the difference between linear and nonlinear functions and try to visualize them. Look at these two graphs. The one on the left shows a linear function. See how it forms a perfectly straight line? This means that as one variable increases, the other variable increases at a steady, unchanging rate. The graph on the right shows a nonlinear function. That curve tells a different story. Here the rate of change between the two variables isn't constant anymore. It might speed up or slow down along the way. Okay, why does this matter? A lot of basic economic models assume linearity. Prices go up, demand goes down in a predictable way. But the real world often isn't that simple. On the other hand, nonlinear functions let us model things like diminishing returns or when the relationship between variables suddenly shifts. Now let's consider a simple example equation: y is equal to 5 plus 2x. Remember, linear equations give us straight lines when we graph them. Here's a table showing some x values and what y values the equation gives us. Okay, so you simply substitute these x values and get the corresponding y values. See how for every one change in x, y changes by 2. That consistency is the slope in action. It is important to remember that in a straight line, the slope stays constant. Also notice where the line crosses the y-axis, that's our y-intercept. And in this equation, it's 5. That tells us where the line intersects the y-axis, where x takes the value of 0. Alright, now let's get a feel for the different types of slopes we can possibly encounter. In the first chart, see this flat line? It means there is zero change in our variable y, no matter how much our x changes. Think of a fixed monthly fee, for example. It stays the same even if you use more or less of any service. The second chart is what we usually encounter, an upward sloping line. Positive slope means as x increases, y also increases. A classic example could be as you increase your calories consumed, your body weight usually increases, and there is a direct relationship. In the third chart, the line goes downward. Negative slope means as one variable increases, the other one decreases. In microeconomics, you'll encounter demand curves. Often, these slope downwards. And in the final chart, okay, this one's a bit weird. A perfectly vertical line has an undefined or infinite slope. It means a change in the x variable has a massive immediate impact on y. This is less common in basic economics, but it can pop up here and there in some theoretical models. Sometimes the equations we get in economics aren't neatly arranged to instantly reveal slope and the y-intercept. Take this equation for example, 3x minus 2y minus 5 is equal to 0. Let's manipulate this equation to make our lives a little bit easier. First, we aim to isolate y on the left side. Okay, so we bring 2y to the other side. Okay, so 2y is equal to minus 5 plus 3x. Dividing the equation by 2 gives us y is equal to minus 2.5 plus 1.5x. Okay, now see how we've arrived at the standard y equal to b plus mx form. That means our y-intercept is minus 2.5 and our slope is 1.5. This chart visually confirms what we just found. Okay, the line crosses the y-axis at minus 2.5, our calculated y-intercept. Okay, and the slope of 1.5 tells us that for every 2 steps we move to the right along the x-axis, we need to move 3 steps up along the y-axis to stay on the line. Now let's focus on how to easily find the y-intercept if you're given any linear equation. Remember, the y-intercept is the point where our line crosses the y-axis. A key thing to realize is that all along the y-axis, the x value is always 0. So to find the point where our line intersects the y-axis, we just substitute x is equal to 0 into the line's equation. With our equation, y equal to 5 plus 2x, if we set x to 0, we get y is equal to 5. Our y-intercept occurs at the point 0, 5. This lines up with the graph we've seen earlier. We saw the line crossing the y-axis at 5. Alright, but what if we need to find where two lines intersect? This is common in economics when, for example, we have supply and demand curves. The intersection point represents an equilibrium price and quantity. Here we have two example lines, okay, y equal to 4 plus 2x and 2x plus y equal to 12. Let's use substitution to find their intersection. It's easier to start with the first equation, y equal to 4 plus 2x, that already has y isolated for us on the left side. We'll substitute this entire expression for y into the second equation. That gives us 2x plus y. Instead of y, we replace it with 4 plus 2x. So 2x plus 4 plus 2x is equal to 12, which gives us 4x equal to 8 and x is equal to 2. We take this x value now and plug it back into either of the two original equations. Let's use y equal to 4 plus 2x for example. Okay, if you replace x with 2, you get y is equal to 4 plus 4, which is 8. So there you have it. These lines intersect at the point 2, 8. Okay, we can confirm this visually on the graph too. But on the contrary, what if we know two or more points that lie on a line but need to come up with the equation of the line? Don't worry, we can work backwards to find this. Remember, a linear equation needs only two things, slope and y-intercept. Here's the process. First, let's find the slope. We have our formula for slope, which is straightforward, change in y over change in x. Hence, slope m is equal to y2 minus y1 divided by x2 minus x1. Let's plug in our points 0, 5 and 1, 7. Okay, we've chosen these 2 points. Okay, so 7 minus 5 over 1 minus 0, that gives us a slope of 2. Now we can plug this into our equation y equal to b plus mx. So we have now y equal to b plus 2x. Now we can substitute either of our two known points to solve for b. Okay, if you use 0, 5, okay, now we get b as 5. So for the final equation, we put it all together. The equation of our line now is y is equal to 5 plus 2x. Now let's move on to marginal and average analysis. These are essential tools in microeconomics, letting us understand how decisions made at the margin affect the big picture. Marginal is all about what happens when you add or subtract one more unit. What's the marginal cost of producing one more pizza? Or the marginal benefit of one more hour of study? Average, on the other hand, gives us the per unit view. What's the average cost of production or the average revenue per customer? Keep in mind that what happens on the margin affects the average. A string of low-cost marginal units can really pull down the overall average cost. Alright, let's get practical with the cookie example here. Imagine a box of cookies costs $4, but hey, there's a deal here. Buy a second box and that's 50% off. Sounds really tempting, right? Let's break this down with our marginal and average analysis. The first box is $4. With the discount, the second box adds only $2, making our marginal price at that point for the second unit as just $2. If we buy just one box, our average price is $4. Buy two, our total cost is $6, making the average price per box as just $3. Are you able to spot the trickery with the 50% off here? That 50% off only applies on the margin. Sure, the second box is cheaper and it pulls the average price down. It sure sounds a lot better than saying 25% off, but only if you buy 2 boxes of cookies. And let's face it, were you really going to buy just one box of cookies here? Alright, next let's talk about another important tool for understanding economics, percentage change. This is how we compare how much things go up or down relative to where they started. Here's the formula. Take the difference between the new and old values, divided by the old value and multiply by 100 to get a percentage. Let's use an example that might hit close to home here. Exam scores. Say you started with a 50, studied really hard and raised it to a 70. Plugging it into our formula here, that's a 40% increase. Impressive. But here's the funny thing. Percentages are relative. If you start at 70, a 40% decrease doesn't magically bring you back to 50. You can check the math here, but you can be sure you're ending up with a score which is less than 50. And it means you're suddenly not passing the course anymore. And finally, let's move on to calculus. Let's start by revisiting our friend, the linear function. See this line? Notice how the amount we change vertically, delta y, for every horizontal change, delta x, stays the same. Those deltas represent the change in x and change in y. This consistency is what makes lines predictable. Calculate the slope once and it tells you the relationship between x and y anywhere on that line. Now let's make things a bit more interesting here. Here is a curved line, for example. See how the amount we change vertically, delta y, for the same horizontal change, delta x, depends on where we are on the curve. This is where lines in the real world often part ways. Many economic relationships aren't perfectly linear. This is where we introduce calculus. It's a powerful mathematical tool that lets us handle those curves, figuring out how things change at any specific point and not just the overall averages. Alright, now don't forget about our curved line from the previous slide. If we take 2 points far apart and connect them, we get a straight line. This line is kind of an approximation of the curve's behavior over that stretch, or in other words, the average slope of the curve between those 2 points. Now let's move those points a bit closer. See how the line we draw between them starts hugging the curve more accurately. It's getting a lot better at describing what's happening between those 2 points. Now imagine these points getting closer and closer until they essentially become one single point. The line connecting them morphs into a tangent line at that point on the curve. Calculus tells us that this tangent line slope represents the instantaneous change of the curve at that exact point. Now let's really dig deeper and explore the power of those tangents. See how I've highlighted 3 different points on this curve. Each of those points has a tangent line touching it. Notice how the slopes of those tangent lines are all different. This is the essence of calculus. It shows us that the rate of change on this curve isn't really constant. It might be increasing steeply in one area and flattening out in another area. Okay, I'm going to take this opportunity to introduce a new term here. The derivative of a function gives us that instantaneous rate of change at any specific point. In other words, the derivative is the slope of the tangent line at that point. And finally, a little notation for you. If our curve represents a function like say y is equal to f of x, then the first derivative, which is what those tangent lines represent, can be written as dy by dx. You might also see it as f prime x or simply y prime. They all mean the same thing. So to finish things here, let's see how this concept of derivatives connects to something familiar to us like slopes, for example. In the first graph, the line is flat, representing a constant value of y is equal to 5. No matter how much we move to the right on the x-axis, our y value stays the same. That is, there is no vertical change. In calculus terms, the derivative, which is dy by dx of this line, is 0. The slope of a horizontal line is always 0. In the second graph, the line is diagonal with a clear upward slope. As we move to the right on the x-axis, our y value increases. The derivative dy by dx here is equal to 2. This means for every 1 unit we move along the right, our y value increases by 2 units in a vertical direction. That's the slope here. Understanding derivatives is powerful because they capture how things change at any given point. This is incredibly useful in economics, particularly for marginal analysis. Earlier, we looked at how one additional unit or marginal change affects the overall picture. Calculus, through derivatives, lets us precisely calculate that marginal change, whether it's the additional cost of producing one more good, that is the marginal cost, or the extra benefit gained from studying one more hour, that is the marginal benefit. We've covered a lot about interpreting functions, equations, and graphs, but I want to leave you here with a cautionary note that sometimes graphs can also be misleading. Here's how. Look at these two graphs. They actually represent the same data. See how in the first graph, it has a clear slope suggesting a trend. We spent all this time learning about slopes and their importance. And now I'm telling you that the slope, well, it's all relative. With the second graph, the information shown here is exactly the same, but the vertical axis scale has been compressed. Suddenly the trend seems to disappear and the line looks almost flat. It's all about perspective. Always pay attention to the scale on both axes every time you look at a chart. Another trick typically used is selective data presentation. Imagine a graph showing economic growth, for example, but it only displays the time period that supports a certain narrative, conveniently leaving out evidence that is contrary to this narrative. And finally, smoothing data with moving averages can also be useful sometimes, but it can also hide important fluctuations. So what's the overall takeaway here? Be a critical viewer of graphs. Consider the source, the scale used, and the time frame presented. Don't let graphs manipulate you with the story. Now you have the tools to be your own interpreter and make your own logical deductions. Alright, we've covered a lot of ground in this session on the math necessary to ace microeconomics. From basic calculations and understanding functions to the power of graphs and a peek into calculus, we've built a toolbox for analyzing economic relationships. Remember, math doesn't replace economic thinking. It gives it precision and lets you make informed predictions about how markets and individual choices work. With these basics, you're armed with the tools necessary to tackle a course in microeconomics. Are you ready to get started?